Just in case you needed another run through about the mean value theorem, I thought I'd show you where the mean value theorem applies, what conditions need to be true, as well as how to set up finding the value guaranteed by the mean value theorem. If a function is continuous on a closed interval and differentiable on that same open interval, then at least one tangent line must exist in that open interval that's parallel to the secant line on the function through the endpoints of the interval. Now that sounds like a lot, so with a graph you can probably see what I'm talking about even better. We're given a continuous function. This is a plain old parabola, and our function is continuous from 0 to 3. So that's the part about continuous on the closed interval. And this function h of x is differentiable on an open interval 0 to 3. So that means the mean value theorem applies. We'll talk about what is guaranteed in a minute. So we need a function that's continuous, no breaks, no gaps, no holes. Do you know the calculus definition of continuous? And we need a function that's differentiable, a nice smooth curve. We could take the derivative at any point in order for the mean value theorem to apply. So let's look at a couple of ways that the mean value theorem wouldn't apply. So in this case, the mean value theorem doesn't apply. We're given a continuous function j, and we're given a closed interval 1 to 4. But at 2, j has a cusp. J is not differentiable at 2, so the mean value theorem does not apply. This function h looks like the mean value theorem should apply, but look carefully. H of 1 is way down here. H has a hole at 112. So h is differentiable on the open interval 1 to 3. We could take the derivative anywhere in here between 1 and 3, even at like 1.001. But h isn't continuous on the closed interval 1 to 3. H jumps. I've already drawn a secant line. I'll tell you why here in a second. But h jumps from down here, maybe 1, 1, and then back up to this curve. So I want you to remember this picture whenever you think about the mean value theorem. The mean value theorem basically says if we have a continuous function on a closed interval, we're going to start off drawing a secant line somewhere in between the endpoints of that interval, in this case 0 to 3. We can find a place where the tangent line drawn would be parallel to that secant line. So let's go back to the other two graphs. We drew a secant line between the endpoints of this interval 1 and 4. And you can see the tangent lines would be getting steeper and steeper here and almost becoming vertical at this cusp. There's no place where we could draw a tangent line that's parallel to this secant line. We could draw lots of lines parallel to this secant line. They just wouldn't be tangent lines. What about over here? Well, because we have a discontinuity of h at 1, we draw this secant line connecting the points on h at 1 and 3. We can't draw any tangent lines on h parallel to that secant line between 1 and 3. We could draw tangent lines, they just wouldn't be parallel. So the mean value theorem does not apply. So most often you're going to try to do this mean value theorem stuff algebraically, so maybe it'll make more sense if we use some different notation. So if f is continuous, that's just some function. If f is continuous on a closed interval a to b, that's any interval, differentiable on that same open interval a to b, then at some c, that just means someplace. That's c is an x value we don't know. So at some x value in between a and b, do you recognize this part? That's the slope of our secant line. F of b minus f of a, that'd be y minus y over b minus a. That's x minus x. So we have the slope of a secant line. And then what do we have over here? F prime, that's the slope of a tangent line. So we have the slope of the secant line connecting the endpoints. Has to be the exact same slope as the slope of the tangent line somewhere in between. The mean value theorem tells us that this place must exist. If a function is continuous on a closed interval, differentiable on that open interval, the mean value theorem guarantees there's some place where we can find this tangent line that's parallel to this secant line. And that's not just this function, that's any function. So I'm going to set up number 2 from the Sullivan text. You don't need to go all the way through this. The setup maybe is the hardest part. And so before you use the mean value theorem, you need to make sure the mean value theorem applies. I look at f, and I know f is continuous and differentiable almost everywhere. X, the line, is continuous everywhere. Y equals 2, the horizontal line, is continuous everywhere. This term, 3 over x minus 1, you should recognize as a rational function. It is discontinuous and therefore not differentiable at exactly one place. That's x equals 1. And so when we combine those 3 functions, the only problem place where f is not continuous, is not differentiable, is at 1. That might be a little too much talking, so here's a graph. This is f combined, and you can see at this predicted x equals 1, f has an infinite discontinuity, a vertical asymptote. But we're not concerned about that. We're concerned about whether or not f is continuous on the closed interval 2 to 7. And for sure f is. We can see that on the graph. Is f differentiable on the open interval 2 to 7? Well, we're looking, does f have any cusps, corners, discontinuities in between 2 and 7? Sure doesn't. So what are we going to say? We're going to say, since f is continuous on the closed interval 2 to 7 and differentiable on the open interval 2 to 7, the mean value theorem applies. Well, what does that mean? What are we going to try to find? Somewhere on the open interval 2 to 7, f has a tangent line that's parallel to the secant line on f through the endpoints at 2 and 7. So at 2, at 7, we could draw a secant line, and then somewhere in here exists a tangent line parallel to that secant line. So how do we start off? I meant to have this show up later. There we go. We start off with the slope of the secant line. F of 7 minus f of 2 over 7 minus 2. That's the slope of the secant line. Is equal to the slope of the tangent line of f somewhere. We're still using that same f of x, x plus 2 over 3 over x minus 1. So how do we get f prime of c? Well, we take the derivative of x term by term. The derivative of x with respect to x is 1. The derivative of a constant with respect to x is 0. And you can take your choice. You can do the derivative of 3 over x minus 1 using the quotient rule, the denominator times the derivative of the numerator, minus the numerator times the derivative of the denominator, all over the denominator squared, which is what I did. Or you could think of this as 3 over a function to the first power, which means you can use the power rule. Either way, we get negative 3 over c minus 1 squared. Why c, not x? Well, because we're talking about the derivative of f at some place c, so we put c into f prime, not just f prime. So where would you go from here? You would just do some algebra. This one gets a little bit ugly, so I'm not going to finish. You do some algebra to get c equals some number. What does that number represent? That c represents the x value where the tangent line to f would be parallel to the secant line on f between the points at x equals 2 and x equals 7.